Good afternoon, everyone, and welcome to another Big Data London webinar. Today, we're focusing on Apache Flink. So I'm Andy Steed, Content Director of Big Data London, and joining me today is Nico Kruber from Ververica. So these sessions are designed to be interactive, so please send in any questions that you have using the questions function at any point, and I'll endeavour to ask Nico as many as I possibly can at the end of the presentation. Just one note of housekeeping. If the stream does go down for you, it shouldn't, but if it does, just hit the refresh button on your browser and you'll jump straight back in. However, without further ado, I'd like to get on our main presenter. So over to you, Nico. Thank you.
Yeah, hi, thanks and welcome everyone. Wait, I need to start sharing my screen and present. So as I said, I'm Nico from Ververica. I'm a solutions architect, and we'll like to dig into Apache Flink. I'll introduce Apache Flink, and we'll see how we can leverage stateful stream processing to do some real-time decision making. So a few words about us. With us, I mean Ververica. So Ververica has been founded by the original creators of Apache Flink. It was formerly known as Data Artisans, and we're now a fully owned subsidiary of the Alibaba Group. We actually are also a provider of our enterprise stream processing platform that is called Ververica Platform with Apache Flink at its core. So if we take a step back and think, I mean, we want to talk about stream processing, so we kind of have to get the picture of what is stream processing in our minds first, and what a typical stream processing architecture consists of. So at the start, on the left-hand side here, there's usually something producing the event, an event. So it could be an application that is sending something. It could be a sensor that is generating some reading. It could be anything, basically. It could also be anywhere. So something is creating an event. Then usually you put this event into some log or some stream storage. So typical examples for such storage systems would be Kafka, Kinesis, Pulsar, Pravega, and others. So events basically flow into those logs and can then be consumed by a stream processor. So there, like in the slide, we have 3 different ways of interacting with it. It could be that your stream processor is just reading from that log, doing whatever logic you need to do for your application, and then writing back into the log for further processing by something else, for example. What you could also do is like just read from the log and then put this anywhere else. So you could fill in databases, which you can then use with the traditional systems for doing things like metrics dashboards, or some other further analysis by your data scientists. What you can also do is things like trigger applications directly. So you cannot just write things out into some storage. You can actually also call into other applications or do some notifications directly. And there's a third way, just to complete the picture here. You could read from the logs. You can actually also read from files. You can read from databases. But logs are the typical input for a streaming architecture. You can do your processing and then maybe put things into archives, into files for long-term storage. So those could be typical systems like S3, Hadoop, and other file systems, for example. You put things in there. Those files can then be used where whatever you like. As I said earlier, could be another stream processor, it could be an application, anything. So that's just roughly the high-level view of a streaming architecture. If we now look at some other categories of the stream processing, we kind of tend to put things into those 2 dimensions. One is like use cases that where you need to react quickly. This is kind of the more real-time thing. And the other are use cases which could take more time, more lag time, so we call it. So things where you don't need an immediate response. So it could be things like offline analytics or machine learning and like in model training. So those would be things that could take a bit longer, that you can process, let's say, every once in a while. And then there are on the other side of this scope, you would have things like real-time alerting for fraud detection or security analysis. You could have model serving, or any applications. And there is a white zone also in between, where it doesn't have to be real-time. should also not lag too much. So there's a vast majority of use cases like spreading over those two dimensions, basically. Now let's look into stream processing with Apache Flink. If you look on the Flink website, or if you follow the conferences around Apache Flink, you will notice that Apache Flink, although this project is, let's say, relatively new 2014, quite a bunch of companies and also big companies are using it. So names like ING, like Lyft, like Netflix, the Alibaba Group, and others. So we'll dive a bit into some of those use cases, and then I'll present why they chose Flink, basically, what makes Flink so compelling. So all of those companies kind of process data, and they want to react to those data, to their business data in real time. Those could be things like transactions flowing in. It could be things like events from mobile apps. It could be supply chain updates, IoT sensor data, database updates. So a lot of different things that you can mangle and that you get in most naturally via a stream, because they are being generated continuously over time. And then you get things in, you want to react on them quickly. So some of the Flink use cases from those companies to just show you what it is being used for. So one, Netflix, for example, has various internal use cases, including the preparation of their data feeds for the recommendation engine. And they also have various ETL jobs, both batch and streaming way internally. And with their size and being at the core of the recommendation engine, Flink is processing roughly 3 trillion events per day. And I think that's a measure from 2018, so it might even be more now. Just to give you also a picture of what Flink is actually capable of. At the Alibaba Group, is actually one of the biggest, well, it's first of all one of the biggest real tech companies in the world, but it's also one of the biggest, or one of the companies with the biggest Flink use case, where event stream is peaking at 2.5 billion events per second at their Singles Day shopping event. And this is also when Flink is processing hundreds of terabytes of state at a sub-second latency. With the help of Flink, they were actually able to increase their conversion rate during this Singles Day while using Flink for search rankings and recommendations. Uber, on the other hand, has developed a SQL-based streaming platform that is built on top of Apache Flink. Flink comes with a few different APIs that you can interact with. We'll actually look at this in a second. They chose the SQL APIs as an abstraction that is quite commonly known, that you can use quite quickly, that your data analysts can use. So they developed their streaming platform with Flink at its core. And they have a lot of cross-stream applications in there for doing alerting, for forecasting, and for measuring growth and others. And fourth, just some of the examples. Goldman Sachs has a data lake application data lake warehouse, where use cases where they dynamically generate roughly 120,000 jobs per day. So things are being processed based on the metadata from the data that comes in. And they run also at quite huge data centers, where they actually have 2 redundant data centers to be fault tolerant, and each of which has 20,000 cores, hundreds of terabytes of memory, and 13 petabytes of of disk. In that particular case, they're processing 7 trillion records per day. So this is just to name 4 of those examples. If you actually want to find out more use cases, more about how companies are using Apache Flink, I would recommend looking into the Flink Forward conferences from the past. The videos are online, slides are also there, but I also state a few more of the use cases throughout this talk. So while we have those quite different use cases, like at the bottom of those, at the core of those techniques, there's Apache Flink. We're reading events from something like as I said, could be log stream, could be database, could be anything, and they're also writing things out to something. So at the core, there's always Apache Flink, but there are actually different ways of interacting with Apache Flink, and we kind of identified 3 different personas, or let's say kinds of ways of interacting with Flink. At the let's say very early stages, we had stateful stream processing. So it's a quite low-level API that allows you to interact with streams, with state, and with time. So it gives you full control. On the other hand, there have also been APIs for doing things with SQL. So you can actually write your SQL queries and do analytics with that. So that's a streaming analytics, let's say, persona. And then relatively new, there's a drive for creating event-driven applications via stateful functions. So in the functions way. We'll go through all those three throughout this talk. And we'll start with the streaming analytics. So the first part. So we dig a bit more into SQL and tables. If you think of, let's say you have your data set somewhere on a file, or maybe even it's already a database. So you kind of have a table, and you can execute your batch SQL queries on those. You have a fixed table. You just say like this query, for example, give me the average temperature per room per hour from let's say a table that is made out of sensory data. You just run this, and you get the results into another table that you can persist into database files, whatever. So Flink comes with actually a quite big feature set for SQL. So there's full TPCDS support in Flink 110, and that gives you a lot of options to write your queries that you need for your use cases. But we cannot just do those on batch. It's actually even more powerful, because what we could do is we can see a stream as kind of a table, not as a static table, but as a dynamic table. So if we see the stream on the left-hand side, I have an event that is, let's say, keyed by Mary. So we're looking at users here. And has a timestamp of, let's say, 1st of March 2017. Then Bob is coming in a bit later. Then there is another update for Mary. So we kind of see this is a table. At first, there was only Mary. Then there's Mary and Bob. Then Mary was updated. So it is like a live update to a database. So we call this a dynamic table. So every stream can be seen as a table that is dynamically updated over time. And once we have that abstraction, we can actually also do SQL queries on streams, so on data that is dynamically changing. And what is even more powerful, we can actually use the same query that we had before, that we were running on the batch case, but just do that as a continuously updated query on our dynamic input stream. So we have our input stream that we see as a dynamic table. Then we have the query that is being run continuously. And then we get an output that is also a dynamic table, because it will change over time. And you can do things like update your database with those changes for serving dashboards, for example. Or you can put things into streams, which you can then use otherwise. So same feature set, you just put things onto a stream, you get the same result as with batch. Quite easy, quite powerful. Just to name a few more examples, like when we started, I said like Uber is building their platform based on the SQL offering of Flink. So one of those use cases is real-time analytics. And not just Uber is doing that, there's also Alibaba, there's Lyft, Yelp, and Tencent, and others. So it's actually quite prominent for that. You can do materializing views for dashboards, as I mentioned. You can also do ETL, like both batch and continuous. We saw Netflix and Goldman Sachs earlier that are doing this. And you could also actually do machine learning with this. Alibaba has actually open sourced the machine learning library that you can use in that case. And just to get a bit more deep into a use case, let's say we want to do a customer 360 use case. Somehow we have, for simplicity, only two things that are coming in. So on the one hand, we do have a traditional data warehouse, let's say database, that is hosting our user data, or basically user history over time. and we consume from this database by getting a CDC stream, so change data capture stream that is reflecting all the changes made to the database. So we get the stream, we get this into a log. Then it could be a thing like this table that is mentioned here, that is shown here. Let's say user ID Mary is on a free subscription at this time. At a later point in time, Mary might have changed the subscription and changed to the paid one at 14 hours of that day. On the other hand, you do have a stream of events that is coming in. So this could be like in this example, it's clicks on a website or interactions with an app. And let's say we want to join those two things together to get a better view. So somehow join the click stream that is coming in with the user database that we had from our data warehouse, and create a new table that will contain not just the click stream, but also additional data from our user database. In that case, it would be the subscription that the user had at the point where they clicked this this article, where they had this interaction with the click stream. And in the end, this might be served then into a materialized view for your dashboards or your decisions that you want to drive from those. So when we get things in, let's say at first we have a click stream, we see Mary. Mary will be joined. I mean, this is Mary from 12 o'clock, so it should be merged with Mary's free subscription from 10 o'clock. Then I see the second thing. This will be Bob, also from 12. Bob here is from 11, so that's before, that's fine. It's also joined. And eventually, the clickstream will get to an event that is from Mary, but at a later point in time, so 15 hours. At that point in time, Mary has already changed her subscription into paid versions. So this one should be reflected in here. So we want those streams not to be joined arbitrarily and just get a cross join of everything in there, but we want to join with the state that was there at the time where the event happened. Now we want to do this thing with Flink, and by choosing the interaction with the SQL API, it's actually a quite simple thing. You can really quickly get this done, and I'll show you that now. So it's a very simple SQL query that you need to write, and then you get this for free, this join that is time-based, that is time-consistent whenever you call this out. So you're joining two tables. You say it's a lateral table join based on a specific time in the click stream. And then those are exactly joined together as we mentioned here. The SQL API actually also has a lot more of other functionality like pattern matching and others like windows. But I won't go into this anymore. You'll find a lot of this in our documentation. So this is just to get you started and to see what this can be used for. Now we actually hop on to the next thing, the stateful stream processing. So I said this is a bit more low-level API. It gives you full control over the system, though. In contrast to writing things declaratively via SQL statements, in here you kind of define your data flow. You define your application in a data flow model. So you would define sources, and then you define computations. Each of those computations can have state. State in Flink is always local. Then they can be followed by other computations or transformations. You can join things from multiple streams. You can actually also have timers that would come back at a later point in time, so you can register callbacks into the future. And then there could be a set of outputs. Outputs in Flink are called sinks. As I said, could be a log, could be a database, could be file, could be anything. So this is what you're essentially providing with a DataStream API. And how you do things in there, you write your job in Java or Scala. This example is Scala, so you define the sources programmatically. You say from a stream or batch environment, you add a source. And in this example, I will read from Kafka. Then I will map a line. Let's say I want to parse a line. I do have JSON strings as an input, but I want them as JSON objects inside, so I can do my transformations on a real object. Then there can be other transformations like doing windows, like getting some aggregates for the sensory data that I have here, for example. And then eventually I want to write things out. So this programmatic definition of your job will then be translated into this streaming data flow graph that we had before. So for this example, it would just be the source, then my map transformation, then my window, and eventually I'm writing out things out to a sink. So this is how you define things, and then there are ways to interact with time, as I mentioned before. But we don't go into that detail for this specific talk here. Some of those use cases, things that you can use, that you can do with this. Since it's quite low level, it has nice properties of being quite performant. You also have a lot of ways to express yourself, to do whatever you want. You're free to do whatever you need to do for your use case, for your business logic. And people use this for doing real-time search and recommendation models, or user profiling, like the Netflix example that we mentioned earlier. There can also be, like, traditional companies would also go into learning-based anomaly and fraud detection or settlement dashboards. You can do revenue accounting. You can refine your data and do a lot of things. You can even implement a real an application. Like, there are also examples where there was a social network developed on top of Apache Flink with this DataStream API. So it is very powerful, but it is also low level as compared to the SQL API. Just to give you an example, we actually built a small demo application to showcase how you can use this API to implement a dynamic fraud detection. So at the core, there's Apache Flink, and I'll show you that part in a second. From the outside, we interact with Kafka, which is a log stream. And from Kafka, we get transactions. So it could be, since it's a fraud detection, it's like a banking use case. It could be things like user interactions with your banking website. It could be Swift transactions. It could be cash withdrawals, or anything that is coming in, basically, through transactions. On the other hand, we have a separate team that might define what actually might be a fraudulent activity. So we do have rules that will dynamically change our application at runtime. That way we can react very quickly. So whenever the data scientists in our fraud detection team decide that, or figure out that a certain interaction might constitute some fraud, they would just change the rules. They would add a new rule, and our application wouldn't have to be redeployed. We could change things at runtime and react to this for the next transaction that is coming in, and we don't have to wait for things to get redeployed. In the end, on the output, we will get the alerts that from those transactions that we might want to prevent out. And then for this demo, there are some front-end components that you might want to explore. So if you look into the Flink's blocks, you will find this in there, in a full full explanation of this and of all the components and all the internal details. Just for now, this is how the streaming data flow looks like inside Flink. So for Flink, we call this a job graph. And at the start, on the left-hand side, we do see one source that is basically reading those transactions. So the interactions with your bank, those are flowing in from Kafka. We interpret them by reading those strings into JSON objects, and then like deserializing them, adding timestamps and watermarks and things like that. And on the other hand, we have a second source that is actually reading the rules. So those dynamic rules that make up the core logic of your application. Then we have two boxes in the middle that would do the processing. I'll come to that in a second. And eventually things will end up in a sink that will receive all the alerts. So things that you thought should trigger an alert to someone. Those rules are then actually be broadcasted to your application logic. And this begins, or often, just because we have to wire things up quite statically, and this graph doesn't mean that the whole thing is static. So what we are using here is, for example, a pattern that we call dynamic partitioning. So we do send messages to the appropriate node of the next box based on those dynamic rules. So we don't have to be fixed in how we wire things up on this level. And then eventually we do the evaluation of the rules, and this can also be dynamic. It can be a state machine that is running inside. It could be a machine learning model that is being served, or anything like this. And eventually you might find your alert and would then just put things out there. If you want to know more, I would recommend to look into this blog post. There are actually 2 blog posts in this series out that explain those details, those patterns in detail. For now, let's look into the third persona. So those will be the event-driven applications. This is a relatively new thing that was launched, I think, is roughly 9-10 months ago. It recently got into the open source Apache Flink as an additional library. We call that the stateful functions. And it's a completely different way to how the streaming applications have been implemented in the past. So it follows more this functions as a service model, where you model your application as separate functions, several independent entities that might talk to each other. Actually, they might really talk to each other as they wish. So they can send a message there and they can send a message back. So it's relatively free in how they talk and how the communication is happening. At some point, you will read from something. So you will get your input events for those functions. Those sources are called ingresses, and there are outputs that are called egresses. So each of those functions, each of those modeled, let's say, entities, might have the local state attached. And those states might then also be, or will then also be, snapshots into your stable storage for fault tolerance, just like with a normal Flink API. To compare things here with the DataStream example that we had before. So before we were tied to having a directed acyclic graph, and we needed to wire things up by heart. Now we can just implement functions widely communicating with each other, but those functions will be deployed into a Flink cluster. They will actually be multiplexed in there so that they share resources. So you can use an arbitrary number of functions. You can also make those, so you can also deploy a lot of small jobs. They will share resources. They will be highly efficient. So this problem will be solved in there, and you can actually model the application. Sometimes this is the more natural way to get into things. Or you might just be used to that, functions as a service paradigm. What is also new for Stateful Functions 2.0 is that you can use things like remote functions. So we have everything, your functions, your states, your messages, your streams will be managed and will be executed inside Flink. And then whenever you need to call out to something remote, you do so via HTTP or other protocols, and just send things out. Send a message that you want that the function was sending along with the state. This service can then apply this message to the state, create a new state. This will flow back into Flink, and you get the same fault tolerance guarantees of Flink for the whole thing. It's actually quite neat. And what this enabled is something that I want to showcase in this third example. You can actually include other languages than just Java or Scala. So in this example, we wanted to build something that is doing machine learning via feature vectors and in a multi-armed bandits way. So we might just have some user events that we receive over log. Then we have a few functions that would gather statistics out of those, that would extract your feature vectors. So this will be processed here. Eventually, they will then get into your model that will do your counts, that will calculate the rewards for all those bandits. So there could be a different model for a different user. Like, think of a fraud detection system. You have your transactions coming in here, then you calculate your features, you put this into your model. You might have a different model for different users, because some models work better for some users, while others might work better for others. And then you talk to the external, to the remote function, where you implement this model inside Python. Python is, or seems to be, the more natural way of doing machine learning, or it's actually quite prominent in there. So you just use the tools that you're used to, use the tools that you're familiar with, and you have the distributed nature of your Flink streaming engine, plus the fault tolerance model that it gives you, plus then your usual tools where you do your machine learning in this case. And then you write things out and you react to those. So now that we covered the three basic systems or ways of interacting with Apache Flink and writing jobs in Flink, you might come to the point where you need to deploy things, where you need to put things into operations, to either your testing cluster or your production cluster, or get things out, try things out on a real cluster, not just on your local machine. To get you started very quickly, we developed Ververica Platform. Ververica Platform has Apache Flink at its core, and that makes your life easier. So be it that you're a SQL developer, data engineer that would write their job and just want that to be started to run on your cluster, or it could be your DevOps, a person that will manage the lifecycle of your application, or separate different users or different teams from one another, or interact with the whole deployment in via your CI/CD pipelines, or anything in there. So we built Apache Flink into the core of our product, and we do this on top of your infrastructure. And with that, I mean, we basically run where you run. So we have a very slim list of dependencies for getting the platform deployed. And this is actually a Kubernetes cluster, Kubernetes with at least version 1.11. And then in addition to that, some object storage, which you would need for fault tolerance in Flink anyway. So with just your normal Kubernetes cluster, which can be run in any of your favorite cloud providers or on-premise, like on OpenShift, you can get the platform up and running very quickly, and then get started. At the core of this platform is us managing applications and not just single jobs. So if you think of your Flink job, so you have your code that you've written and you started this in your Flink cluster, then it becomes a job. A job is basically your code at a specific point in time, the state that you're currently at, and maybe some configuration for the Flink cluster. If you now decide to change that application, let's say you are implementing a new feature, or you're changing your job, you're fixing a bug, then you kind of need to stop that job that is currently running and then start a new job, which is your new code, and maybe your new configuration if you needed to change it. And you might still, or you might want to start with the old state. But anyway, it's a new configuration of those three things. And with our platform, we bundle those together into applications. So you're not just managing your single jobs, you're managing your application. So that means we bundle your code, we bundle your configuration for your Flink cluster as well as for your job, and we bundle state. And then you can do things like you're forking off your application. So let's say you have your version 2 here. That is your job, your state, your configuration. And then you want to try and do some experiments. So you want to do A/B testing. Okay, I'll just take this as it was, just fork it off, create a new application based off of the first one. Same job, same configuration, same state. And then change this to maybe run on a different data set and see how things go, or switch a parameter, or things like that. Then maybe you deployed another version 3, but version 3 is not really working as expected. So you might want to go back to the previous version. And this is made simple via the platform. And I'll actually show you that in a second. If you want to get this installed, it's really easy. You just add our Helm repository and then maybe write some configuration changes and just Helm install. Like the full thing, how to get started, is on our website. And you can actually also find a full-length video on the demo that I'm now sharing in a second on YouTube, which a colleague of mine presented during Flink Forward. So let's have a look. What I did earlier is I installed the platform into a local Kubernetes cluster. So if we want to have a look at kubectl and put that into namespace VVP. I installed a few things alongside with the platform, but eventually I will have a pod that is running the platform. And then I access the API of the platform. So this, let me make it a bit bigger so that everyone can see. So this is the platform. Whoops, no, that's too big. So this is the platform's API that I'm showing. And as I said, the platform is there to make things easy for you. So once you have this up, let's actually see what steps are needed to create your job, to put things on a cluster to get started. So what I did earlier is I uploaded an artifact of my job. So this is a job that will actually do some analytics on the Flink's repositories on GitHub. But you just upload your jar file that you built from your development stage, and then create a deployment. So that deployment is the application I was talking about earlier. So I have the deployment, I give it a name, let's say Flink repository analytics. Then I need to define a deployment target. So this is the Kubernetes namespace. This is finally the mapping to Kubernetes namespace where things will be deployed. I provide the jar URL, and if I need to, I can define the entry point class, but this is already defined in the jar files manifest. You might want to add some arguments for your job. I don't need this here. You define your parallelism, default is 1, and I can just start. So there are only a very few things that you actually needed to get started. Just your job file and a few of those configurations, and now the platform will actually get things running. So this is the overview. This is things that I defined earlier, like the jar file and then others I will look at a bit later. If we now look into the events tab, we will actually see what the platform is doing behind the scenes and what it is doing for you. So we just gave it the jar file, we gave it the parallelism, and now behind the scenes it is starting a Flink cluster. So inside Kubernetes, it will spawn up a few more pods for your Flink cluster for this application. And while this is spawning up, let's actually take a look on the Kubernetes layer. So I put this into the VVP jobs namespace. We set the parallelism to 1. So I will have one job manager, one task manager that are running. So now the pods are up, and eventually the job will also be up in those pods, and then I can interact with it. So really easy. While things are still starting up, I can actually show you. I mentioned earlier that this is like we raised the abstraction layer from jobs to applications. So now we can actually, for this application, look into the jobs that were created. And for now, it's just this one job that is now being spawned up. Eventually, as you go through things like upgrades or starts and stops of this application, you will see more jobs popping up in here. Great, so now the application is running. We see the desired state is running, and the current state is also running. So you should see this in the events, transitioning to running completed. And now I can look into metrics for this job, for example. So metrics. Like this is just a bunch of metrics. Now that the job has just started, it doesn't show too much yet. But it will show things like how big have the checkpoints been, how large is the throughput of the job, and others. So typical metrics that you normally want to monitor with your Flink application and to verify itself. You can also look at things like the good old Flink web UI. So this is the plain Flink web UI behind the scenes, but it really is running in those Kubernetes pods at the core of the platform, as I mentioned. And then, let's see about time. So now we have the events. You can also see a look at the job graph in here, which will also give you a few indications of how big the state is, how large the throughput is, and others. So if I now click into this deployment, like those are just easy things to get started. I hope I convinced you with like how easy it is to actually get started with this as compared to setting up the Flink cluster on your own. But you can actually tune a few more knobs. So if you click into the advanced tab here, you will see other things that you can set. For example, how your job should be upgraded. Like usually in a streaming job, you want things to retain states. So I selected an update strategy that is stateful, but you can also do things stateless if you wanted to. Other things that are configured. Since I'm spawning up a Flink cluster behind the scenes, you can select for each and every application that you're running, you can select your own Flink cluster. So you can have one application that might still run 1.9, the other one would be running on 1.10. So you just define those in here. And there are a few more things that just simplify the operations. You can enable SSL, like encrypted communication between all the nodes participating in that Flink cluster with a click of a button, and then the certificates will be created. We will set up actually OpenSSL instead of Java SSL. That would give you 3 times the performance. And or you can configure things that you would otherwise put into your Flink cluster configuration. Since we are running on Kubernetes, you can also define resources. So how many CPUs should each of those job manager pods have? How much memory should they take? Same for the task managers and others. So those are the knobs that you can tune. And if you want to go even deeper, you can actually go into looking at how the REST interface would interact with. So everything that we have here in this UI would also be available in the REST interface. And in there, you can you would interact with YAML or JSON files. And this is the YAML file of that application that we just started. And there you can tune things like Kubernetes pod affinities, or you can set up volume mounts for those pods where you would mount in Kubernetes secrets and others. So those are just a few things. If you, as a DevOps person, want to make things easy for your users, you would just set those as deployment defaults. And I actually already set a few defaults. Like I set a default for the deployment target, so our mapping to a Kubernetes namespace. I set a default for the upgrade strategy to be stateful, and Flink version to be 1.10. So you can simplify things for your users to make this as easy as I presented earlier for getting things started. And then as a user, you don't have to worry about how you get from one state to another. So you just tell the platform where you want things to be, and we'll do everything needed for that. So just to give you an example, I will change the parallelism to 2. I might enable some new feature, enable new feature, and then just get started. So now the platform will see, okay, I need to do an upgrade. I need to do this upgrade in a stateful manner. And that means for Flink, Flink has to take a save point. We have to bring down the old cluster, bring up a new cluster, and start the job from that save point. So all those things will be done for you. If we now look into the snapshots tab, we will see that the save point is being triggered. So we did a suspend that was part of the upgrade, and that was the save point that came with it. And now I think the cluster is already being started. Now we're waiting for the new cluster to be ready. You can actually also trigger new save points. You can fork this application off, as I mentioned earlier. But you just tell the platform what you want, where you want your application to be, and it will get you there. So you don't have to worry. Then one of the nice things that we have in here, let me show you that while the platform is booting up this new cluster, is a restore strategy that we call latest state. That one works with our Flink master failover or high availability configuration based on Kubernetes. And with latest state, it means that we can restart an application either from the latest save point or the latest checkpoint if you know that part of Flink yet already. So a checkpoint is done regularly to overcome your worker failures, and save point might be done manually. So whatever is newer, we will use that when we restore your application. So that one is up now. It got into running. I can create new save points manually, but we'll also see those checkpoints of fault tolerance basis being done over time. But oops, oh, what did we see? Now the job is failing. So we enabled a new feature. That feature is misbehaving, and if something is crashing, then Flink will restart the job. And it is now not too easy to get out of this restart loop. So let's say we were processing some event. That event was just wrongly formatted. So we crash on that. We couldn't interpret that. Then Flink will actually go back in time and rewind everything and start over, where it will see the same event again, and then will fail again and also go back. So now if you want to upgrade a job, you wouldn't normally be able to take a save point because you could just fall into that restart. And this is where the latest state comes in very handy. So we can just cancel the job. We can change our deployment and say we deploy a fix. So a new version of our jar file, or in that case, we just disable that new feature and get things started again. Save changes. Now cluster still terminated. Now we start things up again, and it would use the latest state. And in that case, we don't have a we don't have a save point, but we do have a checkpoint from the past. So if we start this up again, we will just continue from the latest state that we have had before the failure happened. So let me actually go back into the slides. If there are further questions, then we can come back to this later. This will just boot up and use the latest checkpoint in there. So it's easy to get started. It helps you not worry about things. And actually, everything that I showed you here today is part of the community edition of our Ververica platform, which is available for free for any use. You just go on our website and install this. So the community edition contains the application lifecycle management that we went through. It does the configuration metadata management, artifact management, as well as this Kubernetes-based high availability. If you need more things, if you need things like long-term SLA support with off-cycle bug fixes for Flink, or if you need authentication authorization or cross-data center failover, or maybe multi-tenancy support to isolate different teams, different tenants from one another, then you might want to choose our enterprise edition of that. All right, thank you very much. Let's actually have a look whether the job is up and running now. It's now continuous running from that save point, checkpoint, and we're creating new ones. We're making progress with our fixed job. So are there any questions? Let me see. Oops.
So yeah, before we get started with the questions, Nico, I just wanted to make people aware of the fact that this will be available on demand shortly after we finish. So anybody who joined late, maybe missed a little bit of the presentation, or would like to rewind during some of the slides or some of the demo that Nico's just done, you can do so almost immediately after it's finished. Nico mentioned the community edition of Ververica. That, with a couple of other attachments, is in the bottom left-hand corner, so you can go and check that out straight away afterwards. In there also is our upcoming webinar catalogue, so you can see what's coming up and join us again in the next week or so on one of our other webinars. So Nico, I was going to start with this question and maybe tag on a follow-up question of my own. So in data streaming terms, what are the differences between Apache Kafka and Apache Flink? So going back to the beginning, I guess.
Yep. Let me start sharing, maybe get back to the slide where this probably got from. So if we look at the streaming architecture here, like Kafka is a great message broker, so it falls into this category of log or stream storage. It did, however, also add things like K-streams where it can do stream processing. It's not just an object, not just a message broker or log storage. It can also do stream processing. Flink is doing stateful stream processing. It can consume from anything, not just Kafka. It can also write to anything. It is so. I guess this is in streaming terminology the biggest difference in there. So one is a full-fledged mature stream processor, while the other is a message broker that has extended its abilities to do stream processing as well.
Great. And I'm going to. There's a question come through which is very similar to what my follow-up question was going to be, but I'll ask it the other way round. There are obviously things that we touched on one, other services we can use to do a similar thing. Why are people choosing Flink? Why is Uber and Netflix and things choosing Flink to do this rather than other things that are available, do you think?
I think it becomes quite clear from some of the use cases. So Flink is very mature in not just in its API, but also in the whole framework, being able to sustain the applications even at very large scale. So only petabytes of state or billions of events per second. So it has proven to work efficiently there. It has proven to give you the throughput that you need at the latency that you need. So I guess that with the APIs that it offers, so having this like full-fledged SQL, but also low level, but also the new way of interacting with this functions way has convinced people to choose Flink.
Awesome. Is there anything, do you think, that's stopping people using Flink? And you showed how easy it is to get started. Do you think there's anything that's stopping people? And if it is, what's the best way of overcoming that? I suppose I imagine there'll be a few people on the call who are thinking of adopting it, hence why they're here. So any words of encouragement, maybe?
Well, I think with the release of the community edition of our platform, we made it very simple to get started. Once you have your Flink job written in Java, Scala, or with the SQL statements. On the other hand, I think the biggest part in the past was probably people who were using or who were used to doing things with maybe Python for their ML models, and who didn't have a direct connection to Flink, because Flink was this Java Scala world, basically. So using Python in there was a bigger stopper in the past, while we made progress on making both the low-level APIs available, or not just low-level APIs, but the table API, actually, if you know the internals, available for Python, but also via those stateful functions to be able to call into any language into your code that you can write in whatever you prefer. So I guess this has been more of a stopper in the past. Hopefully we made this very simple now, so you can interact with even more external systems, even more languages.
Perfect. Okay, look, I think that touched a little bit on my next question, which is probably going to be my final question, given the time. Or I'll do my question last, and I'll just I'll bring in this question that's just been sent in, just so that it's covered. But you could presumably see it as well, Nico. Does Flink support exactly one message a delivery, or do developers need to track messages a bit like Spark?
Let me read that. Just does exactly once message delivery. Yes, so you can actually configure Flink in different modes. So you usually start off with something that you might call at most once delivery. So without any guarantees, that means you have your Flink's fault tolerance, so the checkpoint's off. So if anything happens, you're back at square zero. Then you can increase that to at least once. So that means every message will be reflected in state at least once. It will be processed at least once. So you have this on the output. And then you can tune this up a notch by setting things to exactly once. So every message affects Flink internals only once. It might be processed more than once, but if there's a failure, we go back in time. We rewind everything to where it was before. And so in the end, we make sure that a message is only processed, or not only processed, they're only affected or only reflected in state once. So that's one thing. And if you want to get even higher, you can set something that we call end-to-end exactly once. So that would include your input, would also include the outputs. And if you were using Kafka, for example, we would make use of their transactions and would make sure that every event is only visible to the outside once we confirmed that, once we have those point-in-time checkpoints, so that it will not be there again. So you have those knobs to tune and those different modes. I hope that answers the questions. So you don't need to track messages. It comes out of the box. You just decide for one of those models, and then whatever you need. So with at least once processing, you can obviously gain more performance because you have less overhead there. But if you really need exactly once, then you just use exactly once.
Perfect. Okay, so yeah, I'm going to add in one more question because it's a very good question again. We saw that the examples you gave before, they were all massive multinational companies, obviously because they're an impressive demonstration of the capability of the platform. Someone's asked about use for SMEs, use for small businesses. Is this a tool for big businesses, or is it something that will be of use for a smaller entity?
No, yeah, you're right. I was just showcasing to just prove how mature Flink has gotten, because, well, just to exaggerate maybe a bit, it is easy to get things done on just one node, on just one computer, or maybe one big machine. But of course, Flink only runs with less than 1 billion events per second. So that is working there as well. And with our platform, you can get started easily, so you don't have to have the whole your whole DevOps team behind to get things started. So I guess with that, it's very suitable for the SMEs. And the programming model is actually quite simple. I mean, I only briefly touched the different APIs, but you have this just you process one event at a time. So that's a huge simplification. If you ever try to write some distributed application your own, you see how much that you don't have to do by using a framework like Apache Flink. So that simplifies you're getting started basically, and getting started from small jobs to big jobs. You can scale out later when you need it.
Perfect. And that did actually answer my follow-up question. So thank you very much for that about the teams and skills and stuff. I think we've I will ask it just in case, in terms of if there's managers watching here, or leaders of teams or whatever. what sort of personnel or skills within their team? Is there anything that they need to be looking out for if they're going to get the most out of Flink? You've talked about some languages. You've talked about perhaps it being a reasonably streamlined team because it's easy to set up. Is there anything else that they want to be looking out for?
Good question. I mean, Uber has, for example, selected to build their whole solution based on SQL because that's a language that the vast majority of people know and know how to write things in. So it can be as simple as that. But if you want to develop your application, maybe your ML application or some things like that, then you might obviously need more knowledge into like the core, so Java, Scala, or maybe Python if you do this stateful functions approach. And then in general, well, you as a DevOps person, you need to know Kubernetes to do troubleshooting to get things started, but not too much. You can also use those hosted Kubernetes solutions by Amazon, by Google, by whoever you want to make business with. So that leverages some of that. So you don't have to worry about that too much. As for developing things, I guess Java helps if you really need to go low level and tune the last bit of performance out of it, for example.
Okay, that's perfect. I think we'll thank you very much for the questions. I know there's some ones we haven't had a time to get to. We'll make sure that they're answered after the call. And thank you very much for Nico for a great presentation and demo. I hope everybody enjoyed it at home. And with that, I think we're going to bid you adieu or auf Wiedersehen, and we'll see you at the next one. So thanks very much to Nico. Thank you, Nico.
Thank you, Andy.
We'll see you shortly, and we'll see you again. Thank you.
Yeah, thanks, everyone.